Zoom tells me that it is live on YouTube, but on YouTube I don't see it going.
Yeah, it's kind of frozen for some reason. I think it's moving just very slowly somehow.
Oh, okay, now it does. Very good. Very good, and I think it's time to start. So I'm very glad to present Yotam Hendel from Northwestern University. He will tell us about singularity properties of convolutions of algebraic morphisms and probabilistic working type problems. Please.
So thank you very much, and thank you for the invitation to speak here. And I think it's kind of useful that you can actually have this title like in front of your face, and then you like don't have to remember it while presenting me. And everything that I'm going to say today is a joint project with Itai Glaser. And I want to start with the following theorem of Lagrange from 1770. And this theorem says that for every natural number x, I can write it as a sum of at most 4 squares.
Yotam, I apologize. I forgot to say that I just shared in chat the file. So everyone is welcome to scroll it on his own.
Okay, good. So yeah, so the file that you guys have has some more remarks than this file, but I will annotate on this file, adding hopefully more things. Okay, so very good. So this theorem by Lagrange, four-square theorem, this is a very famous theorem. And in the same year, Waring posed the following question. So say you take these 2 and replace it by a k, can you still write every number x, every natural number x as a sum of at most some bounded amount of k powers? And the answer is yes, and this was proved by Hilbert in 1909. And now I will present some definition which will allow me to generalize Waring's problem to a more, well, to a setting which I'm interested in. And this is the definition of the convolution. So given 2 maps, one from x to g and the other from y to g, so x and y are just sets and g is some algebraic structure. You can think about it as a group, but really anything with multiplication. So I define the convolution of these 2 morphisms to be a morphism which goes from x times y to g, just by what you'd expect. So x comma y goes to 5x times psi of g of y using the g multiplication. And in a similar fashion, I denote the mth self-convolution of phi as phi upper and this like uppercase star m. Using this terminology, okay, so I guess let's see an example and then I'll say how I can restate Waring's problem. So now say I have some number k, and I just name 5k to be the map sending x to x to the power k, then taking the mth self-convolution of phi k gives me the map which sends x1 to xm to x1 to the power k plus x2 to the power k all the way up to xm to the power k. And in particular, this allows me to rephrase Waring's problem as, do I have some number m such that raising phi k to the mth convolution power, I get a surjective map. So now I can replace. So, and any questions so far? Okay. So now if I have any algebraic structure, I can just ask Waring like an analog of Waring's problem, and just ask how many convolutions do I need for say g to so if I have some phi from g to the n to g, I can ask how many convolution powers do I need to take so that the kth convolution power will be surjective. And we'll focus mainly on groups and Lie algebras. And something which allows me to ask Waring's problem in kind of a uniform or family way is the following notion. So recall that when I say a word, I just mean some element of the free group on R elements. So in particular, one example is the commutator word, and by a Lie algebra word, I just mean an element of the free Lie algebra generated by R elements. So, for example, this guy, and if I have any word or Lie algebra word, I can plug in a group or a Lie algebra and get a word map or a Lie algebra word map. So, for example, if I take the commutator word as before, then any group I plug in, I get a map phi w, which goes from g squared to g just by xy goes to xy, x inverse, y inverse. And I can take the self-convolution of this guy, and this is the same as first concatenating the word to itself and then taking the corresponding word map. So, for example, taking the self-convolution of the commutator word map with itself gives me the map sending x1, y1, x2, and y2 to just the product of the commutator of the first tuple times the commutator of the second tuple. So let me name a few interesting results about uniform Waring type problems. And just to emphasize, so when I say Waring type problem, it's clear what I mean. So Waring type problem is just what you get when you replace natural numbers by some algebraic structure and ask how many convolution powers do you need so that you have a surjective morphism. So I guess first result due to Borel is that if you take any word which is non-trivial, then the word map that you get is dominant when you consider it over any connected semi-simple algebraic group. So it doesn't matter whether this is a really large group or a really small group, it's always dominant, so it has dense image. And in particular, this means that if you take another convolution power, you get a surjective morphism. This follows from the fact that if you have so some open U in G, then U squared is the same as U bar. A second result, due to Larsen-Shalev-Tiep. So if this is in the setting of algebraic groups, this is in the setting of finite simple groups. And it says that any non-trivial word you take has some number depending on W, such that if G is a finite simple group, which is non-abelian and large enough, then taking the convolution power of the word map with itself gives you a surjective morphism. Another type of result for Lie algebras is given by theorem of Bandman, Gurdjieff, Kuniavsky, and Plotkin, and they show that if you have some Lie algebra word map such that the word map it induces on SL2 is non-trivial, then it is actually dominant on any semi-simple Lie algebra G. And there are some non-trivial words which are trivial on SL2, so this is not an empty assumption. And so this is the case of Waring type problems. And today I'm going to talk about a relative analog of this type of questions, which is called probabilistic Waring type problems. And roughly speaking, I can phrase it in the following way. So as this non-precise question, say I have some map going from X to G, just from some set X to some group or some algebraic structure. Do I have some natural number K such that the kth self-convolution has uniform fibers? Now, the good question is, what do I mean by uniform here, right? So this can say different things in different settings. So for example, if I'm in the setting of algebraic geometry, then I can ask all fibers So uniform might mean all fibers have the same dimension, or maybe all fibers are smooth or lie in some nice class of a nice singularity class. If I'm in the setting of finite groups, so X and G are finite, then I can just ask for all the fibers to roughly be of the same size. And something nice about the second item is that I can give it a probabilistic interpretation. So say we are again in the setting of finite sets, and say G is some finite group. So I take nu of X to be the uniform probability measure on X, assigning 1 over the size of X to every element in X. And if I have such a morphism going from X to G, then I can consider the push forward measure on G just using this simple formula. Now, something which is not very hard to verify is that if you first push forward this measure nu of X and then convolve it with itself, this is the same thing as first taking the convolution in the way we just defined and then pushing forward the uniform probability measure on X times X. So roughly speaking, this means that when we take convolution powers, the measure that the push forward measure that we get is the push forward measure of just of the original morphism convolved with itself k times. So just to recap this entire remark, I can rephrase the question of when do I have uniform fibers in this setting of finite groups, and I call it the probabilistic one-type problem, as how many convolution powers do I need to take so that the kth convolution power of phi induces a measure which is very close to the uniform probability measure on G. And when I say very close, for example, so we usually consider it in the L infinity sense. So any questions up till now? Okay. So let me move to the settings of algebraic geometry. And I will consider kind of a general setting, and then in some time I will return to this setting of word maps and Lie algebra words. So the standard assumptions now are that I have some morphism which is defined over Z, and it is dominant because I want to consider this relative notion of Waring's problem. And also I assume that XQ is smooth and geometrically reducible, and G is some connected algebraic group. And I claim that the following two aspects of phi are very closely related. And the first one is the singularity properties of this morphism, and the second one is really the solution to the probabilistic Waring type problem. So you take some family of finite rings, and you see how far is the push forward measure from the uniform probability measure on GA when you vary this ring A over this family of rings. And okay, so I will consider this for two specific families of rings which are of interest. And the first family I'd like to consider is the family of all finite fields with P elements. So in this case, if I have some morphism from X to G, I get this family of morphisms of just maps between finite sets, and each of them has some probabilistic Waring type problem, and I can ask when do this collection of of measures, or okay, you can also think about this as a collection of random walks, is very close uniformly to the uniform probability measure on this family G of FP. Okay, so one fact from algebraic geometry. So if we have a dominant morphism between smoothly reducible varieties, it is flat if and only if the dimension of the fiber equals dimension of x minus dimension of y for all points x in x. And using this characterization of flatness together with the Langweil estimates, we can actually encapsulate a solution for the probabilistic quantity problem with respect to this family of finite fields as saying that you take some morphism and you convolute with itself enough times, and if you become flat, then the corresponding family of random walks is really close to the family of uniform probability measures on GFP. So let me recall the Langweil estimates. So if X is a finite type Z scheme, and I take CXP to be the number of top dimensional geometrically reducible components of X FP bar defined over FP, then these estimates say that the normalized number of points is not very far from this number of reducibility components up to some error of P to -1/2. And this means that in this case, so again, solving the probabilistic Waring type problem, with respect to finite fields, this is the same as asking what is K such that this guy is flat. So any questions up till now? Okay. Now, let us consider a slightly larger or a larger family of finite rings. And now I will focus on the family of finite rings, Z modulo P to the KZ. So this family contains the family that we discussed before. So if I want some singularity property that encapsulates a solution for the probabilistic quantity problem over this family, then in particular, it must also set, like such a morphism must also be flat. And actually, I have some singularity property that really captures a solution for the probabilistic quantity problem in the case of this family of finite rings. And for this, I need some definition. So given some variety x, I say it has rational singularities if it is normal, and if for every resolution of singularities, the push forward of the structure sheaf of the resolving variety has no higher cohomologies. So some example of a variety having rational singularities and some non-example. So if you have the fine variety in an r-dimensional fine space cut out by the sum of xi to the power ni, then this guy has rational singularities given that r is at least 2 if the sum of 1 over ni is strictly larger than 1. So, for example, x squared plus y squared equals 0. So this guy does not have rational singularities, and I think of this guy as some sort of cross, while x squared plus y squared plus z squared equals 0. This guy has rational singularities, and I think about this guy as some kind of cone, taking some nice real form. And the significance of this condition, okay, so one of the reasons for the significance of this condition of having rational singularities is that by theorem of Isabelle and Avni, for local commuter section varieties, having rational singularities is the correct condition which allows one to have a nice generalization of the Langwell estimates to counting points over finite rings of this form of z modulo p to the kz. So more concretely, if I have some z scheme X such that its base change to Q is local group intersection equidimensional, then they show that it has rational singularities if and only if, when I throw out some finite set of primes, then for every k, for every natural number k, this normalized point count is very close to the number of absolutely top-dimensional absolutely reducible components. So now, say we have some map from X to G, then if all the fibers have rational singularities, then we're in position to use, and also I need flatness for my varieties to be local complete intersections, for the fibers to be local complete intersections. And in that case of fibers being having rational singularities and being local complete intersections, we can really use this theorem of Heisenberg and Avni. And this means that we can really characterize some kind of uniform behavior of point count of the fibers using this property. So let me capture this in a definition. So I say that a morphism from X to Y between smooth varieties is FRS if it is flat and if all fibers are reduced and have rational singularities. And really, this is the property that guarantees that all your fibers have nice point count over Z modulo P to the KZ. So it really solves the probabilistic monetary problem with respect to this family of rings that we are interested in. And I guess one remark that I'd like to make is that in an upcoming work jointly with Raf Clackers, we show some relative version of the theorem of Heisenberg and Avni. So in this version, you have some very similar. You get the same result, but now okay. So you get something of this form, and now y is some point in y of z modulo p to the kz. And the important part is that this guy doesn't depend on y, on the fiber we've chosen. So there are some complications with just their proof does not generalize to the relative case. Something has to be done there, and we can show that. And this means that we can really think of the FRS property as the right analog to solving the probabilistic type problem in the setting of this family of finite rings. So, any questions so far before I move to my main results? Okay, somehow this is faster than what I planned, but okay. So, okay, so let me introduce my main results. And throughout this discussion, I assume that either my morphisms are defined over Z or over Q, but everything here has is in the nature of, like, in the settings of characteristic 0. And if I recap what we talked about till now, I have very good motivation to take some morphism going from X to G, raise it to some convolution power K, and ask whether this guy is flat or FRS, or, okay, one can ask more things, but these are the two main properties we are interested in. And getting some K will solve some probabilistic monetary problem. So I guess the first thing one asks himself when you want to take convolution powers is, okay, so say I have some singularity property and I can obtain it after 3 convolutions. Does it make sense to ask that if after 4 convolution powers I don't have this property anymore? And the reality is actually kind of nice. So if I can show that if I have some property of morphisms, which is preserved under base change and under compositions, meaning that if both phi and psi have this property S, then the composition has S. So in that situation, if I also require that the structural morphism satisfies S, then if phi from X to G has S and psi is just any morphism, it follows that the convolution satisfies this property S. So this was something we could show. It's not very hard. And using this proposition, you can show that flatness and smoothness and the FRS property are all preserved under convolutions. And also it's not very hard to, it's kind of easy to see that dominance is also preserved under convolutions. So this question really makes sense. And what we can actually show is that if we start from some dominant map from some smooth geometrically reducible variety X into some algebraic group G, then taking at least dim G convolution powers gives us a flat morphism, and another convolution power gives us a flat morphism with reduced fibers. Another convolution power gives us a flat morphism with normal fibers, and eventually we get an FRS morphism. Now, I guess the naive question is, okay, so all of these 3 only depend on the dimension of G. What about this one? And the answer is that this guy has no chance to depend only on dimension of G, because if we just take f of x to be x to the power n, so the kth convolution power of this guy is this map going from x to the power k to G. So not x, this is even a1. So ak to a1, and just sending these guys to this sum. And as we've seen before, if we consider the fiber over 0, then this guy has rational singularities if and only if 1 over ni is greater than 1. But in this case, this is only the case if k is larger than larger or equal to larger than or equal to n plus 1. And this means that this exponent must depend also on the morphism itself, so it cannot be independent of dimension of G. And also, this is the hard part. Items 1, 2, and 3 are much less hard. Any questions so far? Okay. So let me return to the setting of world maps, and we will actually focus on Lie algebra world maps. So one thing I want to define before I do that is the degree of a Lie algebra world. So if I have some Lie algebra world, then I can consider the natural gradation on the 3 Lie algebra on R elements. So just by how many commutators a homogeneous Lie algebra world contains. And I define the degree of a Lie algebra world to be the maximal grade in which it doesn't vanish. So as a simple example, if I have this word, then this guy has degree 1, this guy has degree 2, this guy has degree 3. So all in all, the degree of the word is 3. And now in these settings, we can show that if we have any Lie algebra word of degree D, then there is some number smaller than 1,000,000 such that for every simple Lie algebra G such that the word map my Lie algebra word induces is non-trivial, we have that after something like d to the 4 convolution powers, we have a flat morphism, and after about d to the 6 convolution powers, we have an FRS morphism. So these results are much stronger than just the general case where we saw that somehow it depends on the group and it depends on the map itself, which is also the case here. But here it doesn't matter whether we consider SL2 or SL1000, we still have the same number of convolutions that we need to take in order to get a flat or an FRS morphism. And this is somehow due to the fact that word maps and Lie algebra words have a lot of symmetries. So somehow you can handle everything uniformly. So now using this theorem, so there was one more remark I wanted to make. And this remark is that it's an interesting question to ask what is the optimal exponent needed here. And one can show that if you take the angle word, so just x and then d commutators with y, then it is not flat after d-1 self-convolutions. So this exponent must be at least linear. And it's a nice question to see what exactly should it be. So one corollary of this theorem 4.5 above is that we can actually get a first step towards solving a probabilistic query type problem in the setting of PID groups. So for this family that I've described before, of finite rings of this form and the maps that they induce when I have some algebraic morphism. So if I have any word of length L of W, I have some constant such that for any connected semi-simple group G, after taking n convolution powers, I get a morphism which is FRS, but this time only at identity. So this means I have some open set inside G to the power nr such that this guy is FRS for every x in U. Now, another remark I'd like to say is that if you are just interested in flatness of group word maps, then this was established quite recently, and this is in the paper of Larsen, Shalev, and Dieppe, where they show that after length to the power 4 convolution powers, you get a flat morphism everywhere, and this is done using kind of a different method than what we're using. So, so any questions before I will talk about the commutator map? Okay. So something additional that we can do using the methods we use to prove this theorem about word maps that I described above, about Lie algebra word maps, is to get better bounds on the number of convolutions we need to take for the commutator map to be FRS. So say W is this commutator in the Lie algebra, then for every semi-simple Lie algebra G, we can show that after 1 convolution power, we get a flat map, and after 4 convolution powers, we get an FRS morphism. And as a corollary, we can show that if G is any semi-simple connected algebraic group, actually I don't even need connected here, then 4 convolution powers gives us an FRS morphism. And so this is an improvement for all types which are different than type A. So in type A, there is some result of Baudour that says that 1 convolution power is actually enough to become FRS. But otherwise, this gives the best known bounds. And actually, this commutator map is kind of the reason this whole project started. And this is due to the following theorem of Isbord and Avni. So they were able to show that if you have some semi-simple, simply connected algebraic group G, and you take gamma to be either some compact periodic group, so a compact open subgroup of GQP, or some arithmetic lattice of high rank, so some GZ and Q rank of G is at least 2, then if the commutator map is FRS after n convolution powers, then there is some constant such that the number of n-dimensional reducible complex representations of gamma is at most c times n to the power of twice n minus 1. So they showed that if you show that the commutator map is FRS after n convolution powers, you get a polynomial growth, a polynomial representation growth where the exponent does not depend on the group. And also they showed that if you take n to be 21, then you get that the commutator map is FRS. So okay, so maybe let me write this. So they showed n equals 21, and later on, Capone improved these bounds to n equals 11, and now we have, in general, n equals 4, so this means that this guy can actually become smaller than n to the power 7. So any questions up till now? Okay. So in this case, I will mention some of the methods, and I think then I will, this is all what I have to say. So the proof of theorem 4.5, so this is the theorem about word maps becoming Lie algebra word maps becoming FRS after something about d to the power 6 convolution powers, can be divided roughly as follows. So first thing we can do is to reduce this problem to a problem about the homogeneous Lie algebra word maps. Then using brute force, we can take care of Lie algebras of low rank. So if the rank of G is at most 4D, where D again is the degree, then we use this result of phi n convolutions is flat if the dimension, so if n is larger than dimension of G, and this should be so we use this result, but on the level of jets. This allows us to take care of Lie algebras of low rank. And okay, so I'm going to mention all these 5 steps. Actually, I'm going to focus on this step number 4, which is the hard part, but let me still go over step 3. So after dealing with low rank Lie algebras, we can encode homogeneous word maps by some combinatorial object and make sense of what it means for this combinatorial object to be flat or to be FRS, and what does it mean for it to be raised to some convolution power. Now, the hard part is to use some sequence of convolutions and degenerations to simplify this combinatorial object so that we get a simple combinatorial object, but which it's still but for which we can still prove it is FRS. But this is once we get to some simple enough object, we can just deal with the problem. But I want to explain a bit about the fourth step. And the first thing I'd like to mention, or I need to define, is that is the notion of degeneration we are using. So what do I say? What do I mean when I say degeneration? So in my settings, I have two smooth families over A1, and I have a GM action which acts on X tilde, on Y tilde, and on A1, and this action is equivariant with all these morphisms. So this is smooth. This is smooth. And in this situation, I say that the fiber over 0 is a degeneration of the fiber over 1. And one thing to note is that because of the GM action, actually phi tilde t is the same whenever t is different than 0. So somehow, for every non-zero t, you get the same thing, and then when you hit 0, the fiber over 0 becomes something worse. And the general philosophy is that when you degenerate a morphism, it can only become worse. So you might have a simpler object, but you pay a price of just having some object with a diminished singularity regularity properties. So let me give some example with just a family of varieties. Then if I consider this family, then when t is different than 0, I get some hyperbolas. And as I take t to be closer to 0 and eventually 0, I get something like a cos, which you can see is singular, where the hyperbolas are not singular. And okay, so I think this is a good example to keep in mind. Now, the mechanism that I use in order to take advantage of these degeneration techniques is as follows. So say I have a family as above, so some family over A1, and I have some GM action. Then if I have some section from A1 to X tilde, and I can show that f of 0, so the degeneration is either flat or FRS at S0, then it follows that f of 1 is either flat or FRS at S of 1. And the way that I concretely use it is as follows. So for this, I need to define one last thing. So a tuple of integers, which we call a weight, gives us some notion of W degree. And this is just, so for every monomial, I define W degree to be the weighted sum of Wi times AI, where AI are these exponents of the monomial. And I define the symbol of some polynomial to be the sum of all monomials of smallest W degree. So this is my way to degenerate. I choose some nice tuple of integers, and then I take the symbol with respect to them, and I get something which, on the one hand, might be significantly simpler. On the other hand, it might not be. It might be much more singular. So, for example, it might not be generated. But I'll have some hopefully illustrative examples soon. And soon is just like below this corollary. And just really what I said, repeating what I said, is that so now I have some morphism between the phi spaces. This is the generality that we need because we are talking about Lie algebras. And assuming that I have some homogeneous polynomials and some weight, so just some tuple of integers, then if I can show that the symbol of phi is flat or FRS at 0, then I can show that actually phi is flat or FRS everywhere. And this is because I can just take some section going from A1 to X tilde such that S of 0 would be, and so in this case, just AN. So S of 0 is 0, and just something like S of t is tx1 up to txn. So S of 1 is this some point I started with. So let me give you an example of how this works, and I think this is all I will have to say. So consider the morphism going from A3 to A2 by XYZ goes to XY times YZ. So this guy is not FRS, it's even not flat, because if you consider the fact, so if both things are 0, you get something which has dimension 2, where we expected dimension should be 1 if this guy was flat. And the reason for the trouble here is that these two guys are repeated. So if I want to show that this guy is FRS, the first thing I'd like to do is to take a convolution power, and this gives me a morphism from XYZ W VU. Okay, so let's try to be consistent. To XY plus WV, comma, YZ plus VU. And now this allowed me to somehow separate these two coordinates, because I will try to choose some weight such that after taking the symbol, each coordinate will have different variables, and this will just be a Cartesian product of morphisms, which I can, and I could take care of each of them separately. So I'd give this guy, so my W will be, I'll give the first guy a weight 1, the second one, like this Y variable a weight 0, so this guy is also 0, and this one will be 1, and so I don't, okay. So this will be 1, this will be 1, and I don't care about these, so they will also be 0. So this is the vector I need. And now if I consider the symbol of my map with respect to this weight, I get something which is much simpler. I only keep the monomials with the least. So I define it as the least. Okay, so let me do something. Okay, so instead of 0 and 0, I probably need something different here. Like let's give this guy 2 and this guy 2, and let's just change all zeros into 2s. And then the only thing I keep is this XY and this VU. Now this is something which is much more simple, and this is just 2 copies of a morphism from A3 to A1 by XYZ goes to XY, and it's not hard to show that taking one convolution power of this guy with itself, so, okay, so you know where this goes. This guy is FRS, so this like X, okay. So, yeah? Okay, so this is something like XY plus VW. And this guy is just a Cartesian power of these two guys, and this is already FRS. So this means that this guy is FRS. And all in all, I can conclude that taking 4 convolution powers gives me an FRS morphism. So this is kind of an easy example, and what can go wrong in the more general setting of world maps is that you might degenerate some maps. So for example, you can think of the map x and x plus y squared. So if you degenerate this guy, you get something which is not generating anymore, and it doesn't have any chance of becoming an FRS morphism. So this is one thing which can go wrong. You degenerate your world map and it does not become generating, so you have to be very careful. And the second thing is that you want to take number of convolutions that don't depend on the dimension of G. So somehow you have to find some process such that no matter how large is your Lie algebra, you can still apply some number of convolutions in order to somehow separate the variables, so you can degenerate. And all in all, and all in all, you will get some uniform results. So the fact that you can actually do this is due to the nice symmetry properties of world maps. And I guess, okay, so this is all I had to say. And thank you. So can a Grosvenor basis technique help here? I don't know. Didn't think about this situation. So can you elaborate, maybe?
So let us first of all thank Yotam. Now please continue with questions. So further questions, please.
Okay, so if you want to elaborate about this Grosvenor basis idea, then.
WIS T?
Symbol seems like taking the leading monomial in term order. So leading, okay, so yeah, monomial of smallest degree, yeah.
So there is, for example, a computer algebra system singular, and they all the time operate with Grosvenor bases, monomial orders, and so on. And this helps to compute things in a similar way to what you do, to consider only part of the expressions and define sometimes an easier variety.
So you probably can read from the Grosvenor basis the symbol. This should be easy. But the question whether you have there more information. But yeah, maybe. So yeah, maybe I don't know what is the like deformation-wise meaning of the next terms in the like the elements in the Grosvenor basis. So maybe that one that asks a question can say about it.
Okay, but I guess one thing I can do is just open Wikipedia and see whether there is something useful to do with this. So thanks for the suggestion. Write it down.
Okay, further questions? Let me ask, so you showed us one application of this due to Eisenbud and Avni. Have you found since then other applications?
So one can, okay, so something else that really follows from this discussion is that if you know that the commutator is FRS after 4 convolution powers, then you have a very nice family of random walks induced by this commutator that you know that are very close to uniform measure. So like you have, say this is your commutator map. And you know this guy is FRS. So you know that after 4 steps, the commutator random walk so one have to be careful when saying like what are the conditions on P and K, probably P large enough in every K, but you can push forward the uniform probability measure on this side, and if you take 4 convolution powers, then for P and K large enough, it will be very close to the uniform probability on G of Z mod PKZ. So really just finding that the morphism is FRS is actually solving some probabilistic quality time problem, and if you have some uniform results as we have here, then it really solves like a whole bunch of family of Waring type problems, right? Because you can vary this P and K, and you get infinitely many Waring type problems in the same direction, and somehow you manage to solve them all uniformly. So this is another application, just this commutator random walk converges. And Itai, if you want to add something.
I will just add that also the result that the word map becomes FRS after approximately the length of the word to some power, to the power of 6. We use it also to show that if you look at the map, so if you look at the probabilistic Waring problem, the Waring type problem on the first congruent subgroups of compact p-adic groups, like like SLNZ. If you look at SLNZP and look at the first congruent subgroup, you can show that the push forward measure will have a continuous density. So usually, if for example you look at the commutator map, the push forward of this measure is usually kind of blow up usually near identity. This is the worst somehow point, and this gives somehow good behavior. The fact that locally around the identity you have this nice behavior gives us probabilistic application to this congruent subgroup. And also so we can say some
upper
stuff
bound on the probability is that you get some element from some word.
Yeah.
So
if
after random walk.
Exactly. If you choose a random element in the first congruent subgroup of some compact p-adic groups, and you choose R elements or whatever, R times and the number of convolution, and you calculate what is the probability you reach everywhere, you get some nice, you get something which is roughly of the same size. So it does not blow up around some point when you.
So there is some correct normalization to be done, yes?
Yeah.
Yes.
To have you can bound in terms of the P you're working on. There is some upper bound on the probability that you give. This is one, and there are all kind of other applications that we didn't discuss in this talk. So we can show using the main theorem about the.
Okay, but this is like more using just the methods, right? Like these are somehow different results, but using the same method. Some bound on low canonical threshold and such.
And I probably missed. Did you mention the associative algebra case also?
No, I didn't.
So maybe it's good to mention it. Okay.
Okay, so you can get similar. So if you have, you can think about the free, just a word in the free associative algebra, and then now I need to remember.
Maybe go to the theorem on algebra, no?
Yeah, this is a good idea. So we can show that if we have W, and this is some word in free associative algebra, so then phi W becomes FRS with just the same, actually the same. So these two bounds, like D to the power 4 and D to the power 6, also hold for words in a free associative algebra. So this is just like n by n matrices. N by n matrices when
polynomials over matrices.
Where k grows. So this guy is.
But not the same n.
What?
But not the same n.
No. I try to avoid this, but not very successfully. So this is either FRS or flat, where n is given as in here. And this is Rn. So this also works for associative algebras, just matrices. And if you want some more precise discussion about really what does it mean for a probabilistic type problem to, like, what is the correct probabilistic language, then we have this in our paper. I just didn't want to mention it too much, but there is more precise treatment of all this stuff of the probabilistic side. So, okay, so thank you.
Okay, thank you again. So next week we will have K-Yuan Chan on the local non-tempered Gann-Gross-Prasad conjecture.
Local not.
Yeah, the restriction for general linear groups when the multiplicity is 0 and when is 1. He has a theorem about this.
אנחנו עדיין מוקלטים?
Yes.
Okay.
But I can stop this.
I think it's a good idea.
Okay.
Okay, so thank you, everybody.